Last month on a Wednesday, 9 o'clock morning, I got a Slack message from one of my consulting firm's CFO mentioning that it's one of its AI systems and cost has been increased from 35k, which was presented or estimated 35k USD per month to 80k USD per month. And they have not included any new feature. The usage was quite in normal level, hardly 15% higher than the previous month, which was quite obvious and acceptable. They even tried some other options, means they tried to use some cheaper LLM model, or they had tried to compress the prompt templates, context templates, but still there is not much difference. It's almost coming the same. So when it came to me as a consulting business, I started digging into its system architecture. Welcome back to a new sessions of Avigya AI Lab. In today's session, I am going to discuss exactly what was the problem of that client, how I started digging up and came to know the root cause of its higher inference cost, and how I updated the system architecture, and what are the next action item for the same solution. Thank you. When I traced back to the system, I realized that the high inference cost was not because of any specific LLM model or due to prompt. It came of the system itself. So this video we are going to discuss how we have to manage the inference cost of a productionized LLM's AI system based on LLM's models. It's not like just to replace one LLM, it's to understand its system architecture. So when the product, let me talk about the product itself. The product was a simple enterprise level Q&A assistant, and it was the internal chatbot. The user has to put some kind of queries, and through the RAG pipeline, the response has been generated and reverted back to the user. The daily load was almost like 30 to 35,000 of user queries. So when I started, the architecture is like this. I am presenting the functional flow of the internal chatbot in the form of simple user flowchart diagram. So user query, then comes the intent detections, retrieve documents, generate answer, evaluate confidence, and return response. Regex architecture is very clean and reasonable. It consists of 6 boxes. The kind of diagram that gets approved in a 20 minute of design review. This is not complex, it's a sequential flow. But when I started digging inside, analyzing actually what happens at runtime, then these are the few, then these are the process, actually the process flow. So the user questions, user query comes. The first one is that first LLM call happens, that is the intent classification. For examples, there are, when the user comes, there will be multiple type of persona. Being one internal chatbot system, then the persona can be from the CFO or the CTO or from the sales, marketing, finance or the customer support. So different persona, different user, is having some intent to get some kind of answer from this chatbot. So the first LLM call should happens like that, intent classifications. What the user is actually trying to know, actually is trying to do, whether that is cost analysis, usage query, customer support request, is related to the marketing, related to some finance support, something like that. And the second is that once the intent classification is done, next is that query rewriting. That means rewrite the user questions into a more precise retrieval query. Because the user gives in some form of natural language, this is also natural language, but how rewriting means what are the different kinds of, say, single query, how the different kinds of queries can be possible, so that even though the user has put one kind of questions, if the some second user puts the different questions, but the answer should be same. So internally we need to validate that it is going and touching to the correct database, correct documents, and then displaying back the response to the user after all the processing steps. So that is the objective of query rewriting. And the next LLM calls that metadata extractions from the user query. If it comes with a specific some attributes, entity extractions or the metadata extractions, so whether the specific nouns, what are the specific nouns are there present, whether time period, any region, any service name, any cloud provider, any specific team name, all those nouns will be extracted. That is called as metadata extraction or the entity extraction. And after that, the next is goes to the vector search. And this vector search, yes, all the documents are stored in their vector database in the forms of embeddings, vector embeddings. So this was working fine, everything was fine. The next, again, one more LLM calls happens, that is relevance reranking. Okay, so the after the vector search, for example, k number of retrieved chunks are retrieved, and which are actually relevant for to answer this user query. So this is the re-ranking. Once re-ranking step is there, and that is also taken care by one LLM. Next is that answer generation. Definitely answer generation is required, so using this document generate the answer, for that LLM is required. Next is that if the confidence evaluation is the answer complete and accurate, that one LLM should be deployed there to evaluate whether the answer completeness or accuracy. So in that case, many systems, they consider LLM as judge, and they compare, okay, with the ground truth value, what is the percentage of completeness and accuracy for that one. Basically based on so certain above the certain threshold value, they deploy that specific AI system into the production. But here sometimes, as part of the continuous monitoring and evaluation, we have to put that LLM continuous evaluation process, which will be online during the online inference process. And if the score is below any specific threshold value, then it will go to the step 2, the query reformulation. Because whatever the query rewritten was there, it was difficult for the LLM to reason or to understand and to take the next steps actions. So if the confidence then 0 specific one threshold, then the complete loop will be initiated. So there are total 7 LLM calls are deployed in serving one user query, and if the threshold evaluation score comes below a specific threshold score, then in that case the one loop will be triggered in order to initiate the process since from the step 2. So you can say, and that possibility is like that in 30% of cases that may happen. So you can say like that total 7.3 LLM calls uh, to serve a single user query. So in that case, if you say like that, the total input tokens is, for example, like 900 tokens for input and 400 tokens for the output. So total in a single LLM call, there are like 1300 tokens to serve a request. So there are total 7.3 number of tokens for the to serve the complete request, a single request, to serve a single request. So when it comes to the 1300 into 7.3, then it is coming around 9.8 k, some 9800, some 700 number of tokens. Due to new customer acquisitions, they had expected that their number of queries per day has been increased from 35k to 85k requests per day. So let's do a simple math behind it to calculate how many tokens are required in order to serve this 85k requests per day by this AI system, internal RAG system. So I came up that 9490 tokens per request in order to serve a single user query when 7.3 LLM calls are involved into this complete AI. So before we fix anything, let's understand the how this token cost mental model works. So think of tokens as a postage stamps, and every time you call an LLM, you pay postage, both for the letter you sent and the reply you get back. Send means the input token and the get back means the output token. And most people optimize the letter. They trim prompts and they compress. And for this intent classification, through some fine-tuned bot or the distilled bot, even the inference time is less than 10 milliseconds on CPU itself. So it's like cost is almost like zero per token cost beyond the compute. There should be some compute cost again on CPU, that is not so much. So we can fine tune one in an afternoon with 500 level of examples. Then next one comes the embedding similarity. Encode each category description and inference time, embed the query and find the nearest category centroid. That works surprisingly well for well separated taxonomies. Taxonomies are like 17 categories. Take the description, embed it, save it into the vector DB. When the user query comes during the inference time, embeddings of user query get a similar cosine similarity with the vector DB contains the descriptions of these 7 categories taxonomies. Whichever will come close approximate, then that will be the category comes. Next one is about the keyword routing with regex fallback. This regex is highly used kind of system, acceptable solution for this. It's like structure enter 70 to 80% can be routed to simple pattern matching through the regex. All these options, the 3 options what I mentioned here, these are the best practices to follow into the production systems. What happens now when we are doing one kind of demo application, some kind of MVP? So in that case, in order to finish the task as soon as possible so that demo can be presented in front of the customer, clients or the senior leadership team, we can use LLMs in all these tasks, but it is too expensive if we start using LLM for all these tasks in the production. So we have to think about how we can do some alternate solutions. Before the invent of LLM, even all these approaches were getting used, and there were also some applications were working fine. It's not like the LLM came and it has done something magically which was not present before. The thing is like that our mind is not open to think about what are the alternates present in this system. So next one is comes about the query rewriting. There also one LLM is one of the most important step, and why query writing is required, because it needs reasoning. A single query, one person writes in a different way than the other person. So what should be the other alternate meanings of the same user query? It has to reason over that one, especially for some kind of ambiguous queries. And have you remember in step 7, if the threshold is coming below, if the evaluation score coming below a threshold, then step 2 comes. So that means query rewriting, intent analysis, all those things. That means the query was not rewritten properly. So this happens in case of some ambiguous queries, but the team was rewriting every query and including ones that were already precise. For example, there is a very simple query: what was the revenue of this specific team last month? So definitely it is a very simple query. Entity extracted for specific team name, last month revenue. There is no alternate disambiguity present in this simple query, right? So better approach in this case is to use one kind of conditional rewriting. That means run a lightweight classifier first. Is the query sparse, ambiguous or truncated? So only call the LLM for queries that score above a threshold or the ambiguity. For the rest, pass through directly. So this actually it may reduce the LLM calls from 100% request to almost like 15 to 20%. Next is about entity extraction. So in a user query, what are the different ways to extract the entities? Here also they have deployed one LLM. So this is a traditional named entity recognition problem with a closely entity set. So we can say that through the natural language processing, when we are doing some project, we were also using speci model with a custom NER model. So here what it says that train on 200 to 300 annotated examples, and for example this is the what is that user query, then highlight all the nouns present here and then extract those entities, and this runs in less than 5 milliseconds on CPU with this 200 to 300. It flows specific document passages. Then in that case uh, it's probably that is in a very good shape. And if the top document similarity is 0.55 and the rest falls sharply, then we need to flag it that okay, it is not retrieval confidence is not working fine. So in that case we can use some kind of semantic entropy. Measure the overlap between retrieved documents and the your generated answer using embedding similarity. So low overlap means the model might be hallucinating. This is deterministic and this is free. So no need of using any LLM here. Next step is we came up with all these 6 areas where we can use some alternate solution instead of directly LLM. So now the next step is that to redesign, to come up with the redesigned architecture. Now this is the new architecture, that is the redesigned architecture, and here the same states are all same, but in each step where before LLM was deployed, now we have deployed its alternate solutions, alternate component there. So what is here? The first one is the user query comes, and there lightweight classifier for intent routing, whether distilled word fine tune on 600 examples. Then conditional branch, if query ambiguity score is greater than 0.6, then query rewriting, the next part is called query rewriting, and that is again one kind of LLM call will be there. If query ambiguity score is greater than 0.6, then only we have to deploy LLM, or else pass through directly through some conditional branch. And the next one is about same for that one conditional, it will be going through the regex entity extractions through the specie NER or the some kind of lookup tables. The next one is about the vector search, and here the retrieval PG vector pinecone will be at same as before. This component, this layer is not changed at all. And the next one is about the reranking of after the vector search retrieval. Then here some macro mini LM L6v2, that is the cross-encoder, is deployed here. And the next part is about the similarity threshold and the relevance filtering. So here discard chunks with cosine similarity less than 0.72, and just for rerank similarity threshold relevance filtering on top of 0.72. Next one is about the answer generation, and here LLM deployment is good, that is full informations. Then retrieval side confidence signal here, that is also some kind of deterministic flow, and no LLM is required here. So, and final response is generated. This is the new revised architecture, and let's now calculate what is the token usage and cost as per this. So average LLM calls per request is now 1.15. Where it is like this response generation, and in step this conditional branching here, and that is also based on some kind of need. It's not that always mandatory in that case. And next yes, accounting for the 15% that triggers query rewriting. And now the math is like that. Before it was 85k request per day, now 1.15 calls, before it was 7.3 calls, and 4050 tokens per call. So it is coming 396 million tokens per day. Okay, versus original it was 806 million tokens per day. So reduction is approximately 51%. Now what I can say is that in practice actually they got closer to 61% reduction, because the single remaining LLM call could now use a conversation history was being serialized and sent 3 times per request. Okay, so one is for intent classifier, second is for query rewriter and answer generator. How this can be reduced? And it is like, for example, it's like same information getting repeated. So what is the solution? Build context once and pass it to the downstream. Okay, so at the start of every request, the orchestrator assembles request context, and this is at the orchestrator level or the supervisor level, that is your agent tags. So what it does is that request context, they formulate one request context, that is a JSON object that contains conversation history, user profiles. For a specific user profile, what is the system context and the session ID, because all this session for a specific user, the session ID, all the conversation history, those needs to be fed to all the three these components, response generator, intent classifier, and query rewriter. So we are building once and feeding 3 to those, and that will be done at the time of orchestration assembles. So every downstream component receives this object and reads from it. Nothing refetches, nothing reserializes, okay? And this also this is also suitable from the caching purpose. If our context includes static components, for example, system prompts, company documents, or the product catalogs, we can cache the KV value, key and value activations for those tokens using prompt caching features offered by this LLM provider, OpenAI, Anthropic, Cloud, all these. So prompt caching, so this Anthropic's, for your knowledge information, Anthropic's prompt caching discounts cached input tokens by up to 90%. And your system prompt is 2000 token, you are running 85,000 requests per day, then caching it saves 2000 tokens into 85,000 requests into 90% discount. That's 153 million tokens of saving per day from one static component. Then you can imagine how much cost we can reduce here, you can save here. Many of the teams, they don't use prompt caching, but we should use. This is must be criteria. This comes under must be criteria. And then I have also mentioned the complete process flow was sequential. Which steps we can make parallel so that we can reduce latency. So one thing is that intent classification and the entity extraction or the metadata extraction, these are two independent tasks. So they both can take the raw user query as input. So we can run these two steps simultaneously in parallel and merge the results before retrieval with some kind of this kind of async. General how we can do through async operation await the proper DAG, that is the orchestrator. So this turns two sequential 500 millisecond calls into one single 500 millisecond step. So here what we have to do, we have to do intent, await, classify, and the entity or the metadata like await, extract, metadata query. And here and some of others like lang graph or the prefect or even async IO that express DAX very cleanly. And this key insight is that the critical path for our pipeline, the longest chain of dependent calls determines the latency. So parallelizing independent steps shrinks the critical path. We have to do that. And the next, again, the architectural principles comes. So what we learned above this, let me synthesize this into set of principles we can apply it to any AI system we are building or auditing. Let's summarize and synthesis all these principles, those we discussed till now, into various principles. So the first one is that principle 1, classify every step by cognitive requirements. That means each node, for each node in the pipeline, for each task in the pipeline, asks the question, does this require synthesis and reasoning or recognition and extractions? Reasoning means LLM is required. Recognitions means some kind of classical ML or deterministic code is required. And most steps looks like reasoning are actually pattern matching in disguise. So when we say that it is some kind of intent classifications, there also we can use some kind of classifier plus some kind of pattern matching. So second one is that count your LLM calls before you deploy. So how many LLMs are getting called? Each LLM call is expensive and it's not per feature, it's per user request. We have to count the LLM cost. So trace a typical request from input to output and count how many times we are hitting the LLM API. If it is more than 2 or 3 times for a singleton interactions, then we have to justify every call. Why we have considered LLM in each of these node. And then we need to find out which are the nodes from which LLM call can be eliminated, right? The third is that build context once per request instead of rewriting for every node. It is like a request context as a singleton. Assemble it at the entry point of the orchestration layer where it is agent orchestration layer and pass it through without changing in an immutable format. And this eliminates the duplications and makes prompt caching work correctly. Next principle is about push intelligence to the edge of your pipeline. For example, LLM should live at the final stage where synthesis is actually needed, not scattered throughout the pipeline during doing things those are simpler tools can do. Right? So response generation is a kind of intelligent activity, and we can do that. We can deploy LLM into all those response generation phase instead of deploying that in some kind of cheaper, faster or more cacheable intermediate stages. Next one is about use retrieval side quality signals instead of LLM self-evaluations. So your vector similarity scores, BM25 scores, cross-encoder scores and citation overlap all on better confidence signals than asking the model to evaluate itself. LLM as judge, when we deploy some LLM as judge, as per my experience, those response, they don't give the score consistently. Same request and response score may vary up and down. So there are some other tricks we will be discussing in some other design session. But here what I mean to say is that LLM as judge deployment is not a wise decision always. Instead of that one, also we can do some other alternates. Here we have said that. Here we saw that how one client inference cost from 80k USD per month is reduced to 31k per month, 31k USD per month. So it was not because of switching the LLM model to a cheaper LLM model or degrading the output response generated or any other compromises we have done in the throughout the complete pipeline, but instead of just improving the system architecture. So most of the now team members they look for quick solutions. So for each step they design one AI system by deploying LLM in each step of the AI system. It's not, they don't validate that whether is it really reasoning required. If reasoning is required, then no doubt LLM is the best tool for that one. But not all the step reasoning required. We can have some alternate solutions. Until this time also, we have our existing machine learning, deep learning architecture, the components which we can deploy in each step instead of writing a simple prompt, because many engineers, they are comfortable in writing a simple prompt rather than writing a classifier, writing a code. But that will increase the intelligence of the system, the scalability, the robustness of the systems, as well as it will reduce the inference cost. So in my next session, I will be covering the follow-up of this. What are the 5 mistakes, what kind different kinds of errors you used to get in an AI system in the production environment. If you liked this session, then please comment me what kind of AI system architectures you are building, so that I will also get some topic on which specific area I have to prepare my next video, learning video. And please don't forget to subscribe, comment and hit the like button for me. This will be keeping me motivated to generate to come up with some kind of new architectures or the new tutorial video. So thank you for watching this video and keep it up. Thank you.